Hello, my name is Aaliyah, and I'm here to help you with some production and operations management topics. Today, we're going to do a few problems about expected value, capacity planning, factor rating system, load distance models, and break-even pricing. So, our first question is, a firm must choose between remaining where it is with current capacity and building a new facility with 50% more capacity. The probability of high demand is estimated to be 75%. So, just to give you some background, expected value is the sum of all possible outcomes, each multiplied by their probabilities or the probabilities of them occurring. So expected value is very helpful when figuring out what decision you want to make. You can map out expected value by using a decision tree, which is helpful if you want a visual of like all the different paths you could take in a process. But today I'm just going to answer this question by using a simple formula, which I stated before is the sum of each of the outcomes multiplied by their probabilities. So, as we stated in the question, the probability of high demand is estimated to be 75%. So, we'll just put P, which stands for probability of HD, equals 0.75. Or 75%. And so the current facility would provide, so we have a current and a new facility. So let's write current for current facility. Current facility would provide $100,000 profit if there is high demand. So I'll put current of high demand equals $100,000 profit. And then it also says if there is low demand, the current facility will yield $50,000 profit. So we don't have a percentage value given to us for low demand, but we can automatically assume that since there is two outcomes, that the probability of low demand is 1 minus the probability of high demand, or 100% minus the percentage of high demand, since both outcomes, the probability of both outcomes must equal 100. So here we're going to write the probability of low demand equals 1 minus 0.75, and that would give us 0.25. So, and we stated before that the current facility would yield $50,000 if there is low demand. So, So the replacement facility or the new facility would provide $160 million profit if there is high demand. So I'll put new to represent the replacement facility. New of high demand equals 160 million. Oops, I'm missing some zeros. And then new low demand, so it says it would only break even if there's low demand. So break even, the definition of break even is basically the point at which you are not making profit yet. You're making just enough revenue to cover the cost of goods sold, or the cost of goods sold plus your fixed cost, so your total cost. So so if we're not making profit yet, we can assume that the profit for low demand would be 0, or the profit at low demand would be 0. So what is the expected value of expanding? So expanding into the replacement facility is this new facility right here. So we're gonna use this information here to create our formula to solve this problem. So we take the outcome of high demand times its probability. So 160 million times 75%, or 0.75. And then we add this to, and you can add in some parentheses to keep everything nice and neat so you don't get messed up. So the probability of, or the outcome of low demand times its probability, which is 25%. So here we have 120 million plus 0. So we have 120 million here. And that is our answer to the expected value of expanding. Our next problem asks us, what is the expected value of not expanding? So that's this current facility here. So we're gonna go in and do the same thing. So the outcome of high demand, so that's 100,000 times the probability of high demand plus the outcome of low demand times the probability of low demand. And this is going to give us, so that would give us, 75,000, and gotta do quick math for this. So this would give us 120, or 12,500. And so that together would give us $87,500. So that is the expected outcome, or the expected value of not expanding, keeping the old facility or the current facility. So continuing from, this is the third question, continuing from 1A and 1B, should the firm expand? So if you were a business owner, would you rather expect to make 120 million or 87,500? So the obvious answer here, since 120 million is greater than 87,500, we would go ahead and expand. So the answer is yes, we should expand. Okay, so question 2A is asking us, a clinic has been set up to give flu shots to the elderly in a large city. The design capacity is 50 seniors per hour, and the effective capacity is 44 seniors per hour. Yesterday, the clinic was open for 10 hours and gave flu shots to 330 seniors. What is the design utilization? So design capacity is basically, if you have a facility, the design capacity, or a facility or machinery, the design capacity is basically the maximum capacity that machinery or equipment or facility is designed to yield. And effective capacity is how much this facility or equipment can yield at an effective, sustainable rate. So utilization equals, gives us a percentage that tells us how much we actually output in comparison to how much the facility was designed to yield or could effectively yield. So there's two types of utilization: design utilization and effective utilization. And we can get both by plugging in either design capacity or effective capacity into a formula. So this is our formula. Utilization equals actual output rate over capacity. So if this is asking for design utilization, we can go ahead and create a new formula that is specific to design utilization. Design utilization equals actual output rate over design capacity, since we are trying to find design utilization. So our DU, our actual output rate was given as the clinic was open for 10 hours and gave flu shots to 330 seniors. So that's given as a total value per 10 hours. But our design capacity is given to us for 1 hour. So we need to do a little bit of math here before solving this question. So if our design utilization, we could actually plug it right into the formula. So our design capacity is 330 seniors for 10 hours. So we can go ahead and divide that by 10. And this is our design, oh no, sorry, I messed up. All right, let's try that again. So our actual output rate is the 330. Output rate per hour is 330 per 10 hours, which would give us 33 per hour. And we can go ahead and just cross that out. And then in the denominator here, we have our design capacity, which is 50 seniors per hour. And we actually were able to fulfill 33 seniors per hour. So 33 out of 50 is our design utilization. So I'm just gonna plug that into the calculator to get a percentage value. And it is 66%. So our design utilization is 66%. So the next question is asking us, what is effective utilization? So we're gonna do the same thing. Effective utilization equals actual output rate, but over effective capacity instead of design capacity. So what we can do is just go ahead and plug this 33 back in for actual output rate, and then our given effective capacity is 44. So this would give us 3/4 or 75%. So this is our effective utilization. So continuing from 2A and 2B in the clinic, is the clinic being underutilized? Could this clinic sustainably give more flu shots? So this hint of sustainability lets us know that we need to know if we are meeting 100% effective utilization of our facility or machinery or whatever. So because our effective utilization is at 75%, we actually could increase our production more. So we are not, the clinic is being underutilized. It is not effectively meeting capacity. Now, if we're at 100% effective utilization, but we are still under on design utilization, the clinic is not being underutilized because we could not sustainably make more, even though the equipment or facility was designed to do more. But what really matters with sustainability is effective utilization. So yes, the clinic is being underutilized. So our next problem is about the factor rating system. So Medco plans to open a new medical care center and is looking for a suitable location. They have narrowed their choice down to 3 locations: Oak, Elm, and Ash Streets. They have defined 4 factors and have assigned weights to these factors as follows: proximity to hospitals, which is 40%. So I'll just put proximity to hospitals, 40%. Customer parking, so CP is 30%. So in the question, these values are actually given as just 40 and 30, but all of these values given for each one of these, the sum of all of these percentage, or the sum of all of these coefficients, I'll call them, always will equal 100, because what the factor rating system does is assigns different values to different qualities, and then based on how you rate those qualities, they're weighed heavier. And ultimately, when you add up the sum of the weights times the ratings, you will get an overall rating for a certain location or one of the options. And then this way you'll be able to figure out which option is actually the best based on your weights, what's most important, which characteristics are most important to you. So back to the question, customer parking was 30%, appearance, so A is 20%, and you can write this out. I just find it easier just to use shortened variables when doing so much math. So our ease of expansion is 10%. So they rated the 3 locations for the 4 factors using a scale of 1 to 5. So we have 3 locations, so I'll just draw out the chart here. Oak, Elm, and Ash are 3 options. And here are our characteristics. So for pH, I'll call it, Oak received a 2. A 2. For CP, or customer parking, it received a 5. For A, or appearance, it received a 4. And for ease of expansion, it received a 3. So I'll just go ahead and plug in the rest of the values for Elm. So that's 5, 1, 2, and 4. And for Ash, 3, 3, 5, 1. So these are the values we were given for this problem. So we know now we can just multiply each of the weights by the ratings. So we're just gonna do a 0.4 times 0.4 times 0.4, and then oh no, I did that wrong. And then the value for E is 0.1, and CP is 0.3, and for A it's 0.2. Instead of, or you can say times 20%, but just remember that you're using a decimal here when you're doing the actual multiplication. So then here we can get like a total score of each of the locations by multiplying each of these rows, multiplying what's within these rows, and then adding the sum of each row. The sums of all the rows. So 2 times 0.4% or 0.4 is 0.8. So we have 0.8. And then 5 times 0.1 is, I believe, 0.5. So 0.5. 4 times 0.3 is, I believe, 1.2. Yeah. So 1.2, and 3 times 0.2 is 0.06, pretty sure. Or 0.6, I'm sorry. So same here. 5 times 0.4 is 2, plus 1 times 0.1 is 0.1, plus 2 times 0.3, which is 0.6. And then 4 times 0.2 is 0.8. So, for Ash, 3 times 0.4 is 1.2, and then 3 times 0.1 is 0.03, or 0.3, I'm sorry, plus 5 times 0.3 is 0.15 or 1.5, and then 1 times 0.2 is 0.2. So we're gonna add up all of these to get our final value or final rating for each one of these locations. And the rating will always be out of 5, because I believe that is our maximum here. Yeah, they were all rated out of 5, from like 1 to 5. For each one of these characteristics. So our total rated weighting for each one of these locations is going to be out of So this 1.3 plus 2.5, 3.1. So our total rating for oak is 3.1. So this is 2.1, 2.7, 2, or 3.5. So we got 3.5 for elm, and then for ash, 1.2 plus is 1.5, 3, 3.2. So we got a 3.2 for ash. So, so the weighted score for oak is 3.1. The weighted score for elm is 3.5. The weighted score for ash is 3.2. Continuing from this, where should the firm locate? So we should choose the location with the highest weighted rating, which is elm. So the firm should locate in elm. So our last topic, our second to last topic, will be the low distance model. So logistics company has just signed a contract to deliver products to locations, and they're trying to decide where to put the new warehouse. The delivery locations are Chicago and Kansas City. The two potential sites for the warehouse are Peoria and St. Louis. So those are the two locations we'll be focusing on for this question. The X and Y coordinates for the delivery locations and warehouses are as follows. So I'll just go ahead and write this chart out, and this was given to us. And from this information, we'll be able to answer the problem. So okay, so these are the coordinates given to us, and then we're also given the total quantity to be delivered to each destination. So 400 to Chicago, or I'll just put the weights here for convenience. So 400 to Chicago and 150 to Kansas City. So the low distance model basically lets us know where we should place something, how far. So if we're given multiple locations and we are expending money and gas and resources, delivering products or transporting products from each location, which location should we choose based on how many times we are transporting goods, or how much goods we are transporting from each of these locations. So the low distance model takes in all of these factors, not just the distance of the location, but how much of a load we're actually transporting to each of the locations, so we can select the best location that represents the most centered location to reduce the cost of transportation and shipping and all of that. So our question is asking us, what is the Chicago-Peoria load distance? So here, to find the distance between Chicago and Peoria, so we can take the coordinates 92, 42, and Peoria, and we're just going to subtract those coordinates. So 90, 41. So the way we're going to do this is the coordinates for Chicago, this is the coordinates for Peoria, and then here we're just going to subtract x2 from x1 and y2 from y1. So the difference between 92 and 90 is, and then also if you're subtracting, if your x2 or y2 is greater than your x1 or y1, just go ahead and take the absolute value. So because it isn't possible for us to get a negative value for our answer. So we're always taking the absolute value of the difference to get our final distance. So the difference between 92 and 90 is 2. And then we're gonna add that to our y2 minus our y1, which is 1. So the distance between Chicago and Peoria is 3, but we're going to multiply our load by the 3. And the loads kind of act like weights. So this is a little bit similar to our factor rating system, since the weights affect our outcome. So our 3 times 400 is 1,200. So that is our Chicago-Peoria load distance. So I'm just going to go ahead and do that. Do the same for the rest of the problems. So I'll put Chicago CP there so you can know what that is. So what is the Chicago-St. Louis load distance? So C St. Louis. So we're gonna take our coordinates again, 92, 42 for Chicago, and then we have our coordinates for St. Louis are 90, 30, 39, excuse me. And so this would give us, so 92 minus 90 is 2, 42 minus 39 is 3. So this would give us 5, and we can multiply this by our 400 load distance, or our 400 load or weight, and this will give us 2,000. So what is the Kansas City St. Louis load distance? So Kansas City to St. Louis. So we're going to take our Kansas City coordinates here is 85, 39, and minus our St. Louis coordinates, 39, and this is going to give us 85 minus 90 is -5 or 5. Remember, we're taking the absolute value, and then we're going to do 39 minus 39 equals 0, so 5 times the weight for Kansas City now. since Kansas City is involved, Kansas City, we're shipping 150, for example, 150 toys. So from Kansas City to St. Louis. So we're going to multiply the 150 toys times our distance, or in a real life example, our distance of 5 might be 5 miles, you know, we're just 5 units away from St. Louis in Kansas City. So 5 times 150 would give us 750. And so that is our low distance score for Kansas City, St. Louis. And then lastly, we have Kansas City, Peoria low distance. So Kansas City to Peoria. So again, with our Kansas City coordinates minus our Peoria coordinates, and so we have 85 minus 90. Again, absolute value is 5. And then 39 minus 41, absolute value is 2. So 5 plus 2 is 7, times our Kansas City weight is 150. 7 times 150 is, don't know this by heart, so I'm gonna look it up. And so we have 1,050. So these are our low distance scores for each of our pathways or distances. So should the warehouse be in Peoria or St. Louis based on low distance? So what we can do is go ahead and add our Peoria and St. Louis low distance scores together. So for Peoria to, or Chicago to Peoria, we initially got 1,200. And we can go ahead and add that to our Kansas City to Peoria low distance score, which was 1050. So here we're gonna get 2,000 and 250. So this is our total low distance score for Peoria. So, and then for St. Louis, our total low distance score would be the Chicago to St. Louis was 2,000, and then we're gonna add that to Kansas City to St. Louis, which was 750, and we're gonna get 2,750. So this is our total load distance for St. Louis. So should the warehouse be in Peoria or St. Louis based on load distance? So we have a heavier load distance score in St. Louis. So we're going to choose St. Louis for the warehouse. And then our next question is asking us, what is the center of gravity between Chicago and Kansas City? So I'm going to visit my notes. And the center of gravity is basically, So we chose St. Louis because it had a heavier score, but St. Louis is actually not directly like where the facility should be. But if we had to choose a location for the facility, we would choose St. Louis out of the four. But the center of gravity is identifying the exact point, the exact center or location where we could put a facility for to minimize our costs, to achieve minimum costs of shipping and all of that. So to get our center of gravity, what we will do is oh, okay. So we multiply their coordinates by the weights, and then we add these together, and then, okay, so for Chicago and Kansas City, so I'm gonna write this out to give you a visual. The sum of xi times times load I, and then we have the sum of the y coordinate I times the load I. So Chicago, the x coordinate for Chicago is 92, and we're going to multiply that by its weight. So the weight we got for Chicago is 400, and then we're going to take the y coordinate of Chicago and multiply that by the weight, and then we're also going to take the x coordinate of Kansas City and multiply that by its weight, and then the y coordinate of Kansas City and multiply that by the weight, and then here we will get, if we add these two together, we get 49,550, and then here we get 22,650 as our answer. And then we're going to take the 49 and 550 and divide that by we divide that by the sum of both weights. So the weight for Chicago and the weight for Kansas City, the sum of both of these here, we get 550. So we will take the 4950 and divide it by 550, and then take our 49,550, and then we're going to take our 22,650 and divide that also by the sum of both weights, and then here we will get a x coordinate of 90.09 and a y coordinate of 41.18, and this is, my friends, the center of gravity. So that is the answer to that question. If we had a facility, these are the exact coordinates at which we would place it to minimize shipping and other expenditures, or whatever you call it, expenses for transporting goods. So, or transporting the toys, if we're sticking with our example. So our last and very last question has to do with break even. So this is going to be our easiest problem. So RAISA's Early Learning Center must decide how many students they need to enroll to make a profit. There's a trade-off in quality of care in the number of students enrolled. They must make a profit but not have so many children that the care suffers. They must establish the point where the number of enrolled students establishes the first profit point. They've determined that their fixed cost is, so FC for fixed cost is $4,500 per month, and it costs them additional $150 per month. So not our fixed cost, but let's say our I'll use indirect costs, so or cost of goods sold. So because it costs them an additional $150 per month for each enrolled child. So I'll say cost per child, CPS. That sounds funny because of Child Protective Services. But cost per child, how ironic, or how coincidental. So we have a cost per child of $150. They only enroll students on a monthly basis at a price of $450. So let's say profit or revenue per, oh wait, no, I said cost per service. I meant to put cost per child, so that it's not an acronym for CPS. Okay, whew. So cost per child is $150 and revenue per child is $450. So how many students must they enroll before they start making a profit? So like we discussed before, break even is that point at which we are not making a profit yet. We're right at the point where our revenue covers our costs, our fixed costs and our cost per child. So we can solve this by, again, making a formula. So we're gonna have our fixed cost plus our cost per child. So we're gonna multiply our cost per child by a variable because the total cost of all the children will be dependent upon how many children there are, or our indirect cost, our direct cost will be affected for each unit sold or child serviced. So this is going to be our cost, and then our revenue per child also. So we're gonna, so we're actually gonna add a minus here since fixed costs will take away from the revenue, and then also add a minus here for cost per child. So this is a minus. And then we're going to add in our revenue to counteract our fixed cost and cost per child. So we're gonna have a 450x here. And you can really solve this by using a calculator, but I'm gonna do it out by hand. So what is the point at which 450x will equal our fixed cost? So basically what I did here was just this setting this equal to 0, we can just move our revenue per child. We can move our fixed costs and our cost per child over to the other side of the equation so we can solve it. So here, well, actually we're gonna move this back. So if we move this back, we can get 450x minus 150x to get 300x equals this here, 4,500, and then we can take this, isolate the variable, divided by 300, and this will give us 15 or negative 15, but I mean, if we really move this to the other side of the equation, guys, it's just 15, or take the absolute value of that. So at 15 children, we will be breaking even and we'll be able to cover our costs. So what I'm gonna do for you, since that was kind of sloppy, is I'm gonna plug this back in so you can see how this actually works. So this is our equation that we were initially given. So 450 or 4,500 plus 150x. So I'm gonna plug the 15 in for x that we just got, and then plus 450 times 15. Oh, these are actually minus. This is a minus here. And then this should give us a 0. Since our fixed costs and cost per child, which are negative, should equal our revenue per child, which is positive. So these should balance out to 0. So here we have 450 times 15 gives us 6750. 150 times 15 gives us 2250, and then, or we can minus that, and then we could just go ahead and just move this down, this 4,500, and then if we add the 4,500 to the 2250, we get negative 6,750, and then we add this to our positive 6,750, and we get 0. So this is our break even. So that was the last problem. Again, we covered expected value, capacity planning, factor rating systems, load distance model, and lastly, break even. I hope you enjoyed this video. I know it was like all over the place, but I was able to complete everything. I hope you were able to understand, and just make sure you work everything out step by step so you don't get caught up on small math mistakes like me. And also make sure you're doing things twice, or plugging an answer back in after you get your answer to make sure that your answer is correct. So thank you for watching, and bye.